So we have a few announcements to start the class. First is we had a slight change in schedule, and hopefully you saw the email that I sent last class. So today, Ramon will be discussing several different approaches or schools of mapping, and with many examples. And keep in mind, you should be working some good energy. So we've been seeing on this second mapping project. Like last time, Ramon and I are ready to help you do some georeferencing. We know that a couple of the map locations, really, we have to do georeferencing before you can do much. So we hope to hear from you guys soon about what areas or extra areas that you would like to be georeferenced. And also, so next week on both Tuesday and Thursday, we will have check-ins. So Tuesday will be Daniel, Jackie, John, Joe, and CJ, as I put it in the email. And then Thursday will be the rest of the class. That's Lori, Alana, Rachel, Jenna, and Sean. And so definitely by Tuesday, and even more by Thursday, you should have spent at least 4 hours, so your first week of mapping. And in your slides, like to see brief discussion of what type of data you're using. Your 2 hours of mapping, where you're looking really closely at the geomorphology, mapping it, or the landscape morphology to gain the context to your mapping area. And then a third, we'd like to see a preliminary fault map, with the understanding that you may change, particularly the fault map, as you progress. And just to keep the schedule in mind, the final reports for the second mapping project are due 4 weeks from tomorrow. And at ASU, it's a very hard deadline. So actually still waiting for a few reports to come in from the first set. But for the second set, it's really important that your reports are all in on time. All right, that's the announcements. Does anyone have any questions? All right, Ramon, start when you are ready.
Okay, sorry, I'm just, okay. This is kind of rapid fire developed present lecture here, but what I want to do is we're talking with the instructors, and we, so you're recording, right, Chelsea? Not
Yes.
that I'm so clever in all of my presentation, but discussing with the lecturers, what we felt was, the instructors, we felt that you guys are doing great work and super motivated, and we're really appreciative of that. But we want to also, in the second round of mapping, work to sort of bring the products a little bit closer to kind of professional standard. And this isn't in the, like, criticizing what you've done, but more motivating a sort of refinement towards the products that we can use for the goals we intend, which are to have this fault line work, you know, be used as kind of a test for the potential for future rupture. And so, you know, what we've done and kind of bringing everybody up to speed. Remember, we had our early lectures kind of getting you to think about like structural geology, about and then we did the exercises with the morphologic mapping and then quaternary mapping. So those are the key ingredients. But one thing we didn't have time to do was sort of show a lot of examples of maps that might help inspire you as far as how to do your work, especially now that you've had this experience so far. You've done it once. So you know, so I put this together, and please interrupt me as we go. Also, instructors, please interrupt. We just decided to do this on Tuesday, and I actually didn't have a huge amount of time, so I sort of put everything together here, but maybe it could be more refined. But I do want to acknowledge the colleagues for their input. So, the question that we're trying to ask, something like, what's the fault rupture hazard at sites near active faults? The first step is what we're doing in our class, which was to map fault traces and deformation zones active in the recent geologic past. So a couple key points there. The main one is map traces, so that's lines, and then deformation zones, which could be polygons. So we know that not every fault trace is super narrow. We know there's distributed shearing at the surface, and we might want to capture that. And then the other keyword is active. What does that mean? And so we say recent geologic past, and I'll remind you of the geologic timescale, but this is something like active in the Holocene or the late Quaternary, or even just the Quaternary, but not always much earlier than that, although sometimes we have to go into the Tertiary, so the last 50 or so million years, but mostly we're thinking of the last tens to 100,000 year time scale. So the only way we can really get that is to understand the Quaternary geology as it might be related to the fault traces. So let's look at this as one example that Tim provided as a kind of a cool way to build one of these fault maps. And so this is an example. Jerry Tryman, who is a well-known and sort of veteran geologist working for the California Geological Survey, and this is a kind of product that CGS produces, and they're studying the Raymond Fault. So I didn't choose this because Ramon is my name, but it is similar, by the way. It's in LA Basin, and so the main thing is plate 2 is this one. So what I really want you guys to look at, and maybe we can get a little commentary going, is look at what was mapped. And these are this to me is the observations that feed into the fault trace line work. And so what you can see here is it's of course very neatly done cartographically, and much of the work was done sort of air photo based lineaments with different sort of qualities. They have this one symbol here, faceted spur or slope. So it's kind of like a what you guys were seeing, the triangular facets. But you see basically this zone of lineaments, and they're not very continuous. They're pretty broken. And then the other thing we see is this pink, which are these geomorphic features that came from a prior study, but sort of zones of unusual geomorphology, let's say. And so these are this group of features are what then indicate the fault zone. So let's just look a little bit zooming in. So here's the explanation that they used. So, you guys don't have all of the information that others have. Like in this case, there was some compilation, but, scarps interpreted from the LiDAR data, and then the air photo derived work. So lineaments and scarp erosional drainages. The key thing is that it's also fairly systematically presented. So we do want to, and Chelsea will follow up with you guys on trying to standardize some of our cartography so that we're using basically the same line types for similar features. So does anybody want to talk about what their impressions are of this map? Any thoughts or questions?
Well, I'll bring up a point just from consulting practice down in LA. This is Chris.
Yep.
So LA is a highly urbanized area. The city built over all the tectonic features. And one nice thing, if you're working in the LA area, I'm not sure if it was used for this study, is there's a set of early 20th century 5-foot contour interval topographic maps. So that's before people started digging away fault scarps, and anything that was built on the fault scarp. So a lot of geologists that work down in LA area and in other parts of the world use topographic data that predates construction.
Yeah, that's right. I think those were used, and this base map might even be that, or this is at least a mid 20th century topo.
Yeah, I can't remember if one of the oldest topo maps, but certainly one that predates the heavy development of this area. I mean, you can see really old things like the Hotel Huntington, which was from the 1920s, I think. And, I like this example, Ramon, because like you actually can see the tectonic geomorphology really well on this topo base.
Yeah.
A lot of details, I mean, it kind of gives you the gross sense of the fault zone, and then from mapping on vintage aerial photos that also predated a lot of the development.
Yeah, so if one thing that students, we don't have you guys mapping on a lot of contour maps, but our expectation is that you can read the topography from contour maps or from hillshades or from imagery, air photo or satellite based, but you can see this little scarp right here that's broken. There's scarp. So we see, this kind of break in topography. This is a sag pond right here. Now, taken by itself, a pond anywhere, you're like, well, every pond doesn't have a fault going through it, and that's true. So one of the key points is this I keep saying this word ensemble, but it's the collection of all of these features. Any one of them by themselves is not super indicative, but the group together tells you that that's where the fault is. So here's another sag right there. There's this scarp back here is not super evident in these data, but was probably evident in the air photos as a break. And notice it's pointing the other direction. You can tell by the ticks on those lines. Now, one thing you can see as we move along, there's a couple of little ridges along the fault, these little pressure ridges, these elongate highs, which are also, and then, linear slope. So, we're seeing the lines as well as the point features that are part of that. And then, I don't at the moment have the definitions of these codes, but you see there's some different point-based coding that's being used to tag those locations. And for me, the point of the point-based tagging is twofold. One is to show what's there, that it's a sag or a pressure ridge or whatever, but the second is it's part of how you demonstrate the kind of consistent and even coverage of your mapping. As you sort of put something there, it's like your stamp. Yeah, I looked here, this is what I saw. And so sometimes I'm coding just by like putting things there. Stamping means I looked. And if there's a blank spot, then I wonder, well, is there really nothing there, or did you not look? So so that's key. So any questions, any student comments? You guys are becoming real aficionados of this, presenting them or developing them yourself. So any questions or thoughts, lessons for your own mapping?
I had kind of a random question, and maybe Chris knows the answer to this because he's in the industry, but since the goal is to try to maybe determine the level of hazard from this, are you guys using equations or models like we did from Peterson's paper at all, or does it kind of depend on what the goal of the mapping project is?
Totally dependent on the goal of the project. So down in LA, a lot of the studies that would be done are for construction projects to make sure that you're avoiding the fault. So I don't know if the slides that I put in are later included later, but
Yes.
The state of California zones active faults, and within those zones, for any projects that involve buildings that would be, there we go. There's an Alquist Priola zone, as they're called. And so if you're gonna do a subdivision or build any kind of big infrastructure that people would be spending a lot of time in, you'd have to do the kind of study exactly like what you're doing now, mapping out the faults, and then probably confirming your fault locations with trenches, just to say that a fault is or isn't in a certain location, and then you have to set back the active faults that you find. If you're doing engineering design where your infrastructure has to meet some sort of demand, so that demand could be ground shaking or fault displacement in this case, then you'd use those equations to figure out what the displacement would be on that fault. And you'd probably do some additional studies to pinpoint where that fault is located. So there's kind of different sorts of studies that you do and different goals.
Okay, and do models give you a better assessment of hazard, or is that just kind of one thing you can do and there's a bunch of others, and just superficial mapping of faults is also valid?
Well, the superficial mapping, I think, would be the starting point to where the fault is. The models are specifically targeted at the displacement or ground motions. And the most general models are using worldwide data sets of ground motions or displacements and doing regressions. And you say, if I have a magnitude 7 earthquake, what's the average displacement I get for a suite of worldwide earthquakes that have that magnitude? So again, most studies aren't focused, or a lot of studies aren't focused on the actual displacement part. It's mainly just finding the faults and avoiding them. But at PG&E, we've got infrastructure that crosses faults, and we can't avoid them, like gas pipelines. So then we move on to those equations and come up with estimates of what the displacement would be, and then we mitigate the pipeline to be able to meet that demand or meet that displacement without breaking.
Gotcha. Thank you.
Good question, Rachel. So let's just look at these. So to me, what's kind of cool is for you guys to appreciate what you're contributing, where the real hard work is in making this map is one step, is like, what are the observations? And so these are the observations. And then as we go ahead to this would be the inferred fault traces. And from these, we could feed them into the equations that Chris and Rachel were talking about with respect to probabilistic fault displacement hazard, because in a way we already have a probabilistic statement right here, which is that the black lines, especially the solid ones, are the most probable zones of rupture. The dashing would be somewhat less probable. And then the zone enclosed in the purple line is potential for rupture. And outside of that, it's very low. So this is a raw material for that next step. But I think what's key for everyone to take away is that sort of psychological activity of going from your observations to the interpretation. And then also the sort of standardization of the representation. So any comments or questions?
Yeah, this is Rich. I just had one question for Tim, actually. What does WD zone on the previous slide refer to? Do you know?
Remote King, W.
It's Weaver and Dolan. So this was
it's a zone. Okay.
Prior work done by Chris Weaver, James Dolan on the Raymond fault. So when
right.
Jerry did this, he just used their zones. Nothing else.
Yeah. Great. Okay. So what I wanted to comment on for the students was that sometimes it's when you're describing the fault, when you have to write something about it and stuff, sometimes it's really good to just group the fault into zones of similar geomorphology. Like this zone has a lot of pressure ridges and sag ponds. This zone just has kind of subtle lineaments on these types of deposits. And if you do that systematically along the whole length of the fault, break it up into different zones, you have a good map or framework to describe it in words when you're writing about it.
Yeah, that's key. That's right. So it's a convenient, it's basically a segmentation. So we're breaking this up into these zones of common properties that are bounded maybe by important transitions, you know. So this WD zone 1 is adjacent to this Monrovia outlier, which clearly has like some high in size topography adjacent to this fan surface that's smooth, and the fault zone started defining that boundary. Whereas then like WD2 has a couple cool little pressure ridges in it. WD3 is not that interesting. You know, then 3 and 4 have more kind of coming back to this SCART mode, with 4 has the sags in it.
So just a quick question on that. If WD zone 1, if WD zone like 4 had the same kind of geomorphic or tectonic like tracers as WD zone 1 did, would you just call them both?
No, you could say they have similar characteristics, but because they're geographically separated, we'd probably just call them separate zones.
Okay.
The other thing, just a curiosity with respect to what Chris said, is notice how this topo background compares to this one. So this is the kind of modern one. So you can see that all the development there relative to the early 20th century less developed LA area. Okay, so let's keep moving.
I have a larger point there, just quickly. For this class, we're feeding a lot of recent data, so imagery, LiDAR, things like that. But in a typical consulting study, you'll go back to older aerial photos. California has a nice set going back to the late 20s, topo maps, whatever you can find. Again, that just predates any development, may show older features, predates maybe agriculture in some places, just so that the geomorphology may be cleaner or better preserved.
Yeah, and so, whoops, sorry, I just wanted to, and so actually I love to look at maps, maybe many people do, so it's really pretty to see this nice, you know, it must have been extremely time consuming to make this beautiful map, you know, which was done in the 1920s, sort of maybe from air photos plus a lot of manual work. So it's nice. So, okay, let's move on. So the idea was to, we'll have a couple more of these introductory comments, and then we'll just start to look at some examples and take them apart. So first was, I had this nice quote that came from Steve that it's a lot of words, but I think it's pretty rich. So let's just read it together. From the standpoint of improving PFDHA models for hazard, it will be most helpful to have the pre-rupture maps reflect the current standard of practice for mapping fault location, location uncertainty, etc. This standard of practice does pay attention to reasonable geologic constraints and follows well-traveled heuristics or rules of thumb about which features are good proxies for active faulting versus differential erosion not active. So this is a kind of encouragement for us to take our own mapping as we go and sort of move it towards the direction of the examples I'm providing. The comparison of pre and post rupture mapping should be of the objective test for us all to learn how well the fault mapping following our best practices serves as a predictive tool for future surface fault rupture. We want to use this comparison to develop additional data for calibration of the PUFTA models, as well as assess the best approaches for producing useful map data. So this is a very succinct description of kind of what we're doing in our class, and what I'm so happy about that everyone's working so hard on. Let me just read this next one, and then we can open that up for a second. So the challenge for us then is to balance moving our mapping closer to the standards of practice without also introducing too much additional bias. So this is like a general problem for all of education, right? Is we start with young, bright minds, and we sort of frame them into our professional expectations, which is good, but at the same time we might lose or blunt some of the creativity and sharpness that you guys have. So that's kind of how education works, but it's an interesting problem. And so with you all, the students, we have this great opportunity with our motivated group of geoscientists to address these issues. So I don't know if anybody has a question or a comment, or Steve, you want to say anything else? Okay, well, maybe it's fun to let's look at some maps. But so this is just a summary kind of, mapping strategies, guidance, considerations. So we have these generic standards for mapping that we all know of, and we're used to. There's some information that was provided to us by Tim when he talked. There's a McAlpin flow chart that, because there's not really a textbook for this. And so that's a little bit of our challenge, right? Basically, the lesson here is we need to write a textbook. And we know that these fault zones are sort of what we see. The topography is kind of controlled by the slip rate, the fault type, the vegetation anthropogenic changes, and then the current and past processes operating over the surface. So that's what we're dealing with. And then, of course, what this word heuristics that Steve was saying, the rules of thumb, one way we can develop those rules of thumb is by looking at a lot of examples. So let's just look. So one other thing I had was starting to think about how to rate our mapping. So we have some rules, like it has to be a map that correctly portrays the bedrock and quaternary geology. We have to have even coverage. We can't miss things or have sort of imbalance of coverage, and things have to be consistent. So however something's done, it has to be done that way, the same way throughout. And so sort of the bottom line is then how we might judge the mapping is how well supported are the lines that you've drawn by the observations, because we can't sort of rate the mapping by what we know happened in the future earthquake, because that sort of defeats the purpose. So we have to have some other ways of judging the maps, and I think these are the the basic rules, as well as just the assessment of like what's the support for the decision making. So just like the Tryman example, all those observations then fed into the lines that were drawn. So any comments or questions? You guys are awake still? Yes.
I kind of have a question, and it may be extremely silly. Going back on the slide about your standards for mapping, what's the difference between geomorphic and morphologic when mapping?
So the morphologic mapping is what we did, where we just really mapping topographic features. So slope breaks, ridges, valleys, troughs, these really basic sorts of properties. Whereas geomorphic mapping is a little bit of a blend then of kind of what we think the surface processes are, as well as maybe what the quaternary geology is. So if you remember this slide from my intro, the morpho map is on the upper right. So it's really all these sort of topographic properties. And then a geomorphic map would, in my view, be a combination between a sort of the process map and the geologic map is kind of what we would say. So there's sort of what are the processes operating over the surface, but a lot of times that's indicated by what the geology is. So especially as a bedrock versus quaternary units. So any questions on that? That was a good one.
I appreciate the clarification.
Yeah, and I have a slide on that. So, geomorphic mapping, establishing landforms or distributions in relations to each other, process distributions in history, and then quaternary geologic mapping is emphasizing the young deposits and landforms that are usually lumped into one unit in bedrock mapping. It uses both the deposit characteristics as well as the landform shape and position in the landscape as criteria for the unit designation. So, any more questions? I have tons of cool maps to look at, but I want to make sure we're getting some discussion. Okay, one last thing is time. So just to remind you guys, active faults were sort of defined by the recency of last ground deformation. So geologic time scale on the right, Holocene is the last 12,000 years. The Quaternary is the last 2.6 million. USGS quaternary faults have 5 classes: historic, Holocene to latest Pleistocene, late quaternary, mid-late quaternary, and quaternary. And then California Geological Survey, the AP maps go for Holocene if they can, right? We don't always have the dates, but it's something which be the youngest sort of geomorphology and quaternary units. And then Alex was saying that the California Division of Dams has their criterion for active as the last 35,000. So this works when there are ways to constrain the ages, but other times we're just talking about the sort of disruption of landforms that we know are recently active. And so if the fault disrupts them, it must have been recently active as well. What Steve Thompson was saying is, sometimes they don't know, like if you go to places in Australia, these ancient landscapes have faults in them, but there's no age control. It's like since the, Precambrian or something, but we still can look closely, and if we look very close, we might see some even fine scale landforms or fine scale deposits that help us get some age control. So here's just a reminder of geologic time scale. The reason why quaternary matters is 1, because it's near to us in time, but 2 is the great fluctuations in climate over the quaternary basically drive the formation of a lot of different landforms that then are disrupted by faults. So, obviously in high latitudes, that's glaciers and ice sheets, but in low latitudes, it's this fluctuation of sort of sediment supply and transport capacity that drives incision and deposition. So, comments before we look at some more cool maps?
Yeah, Ramon, if you can go back 2 slides, just wanted to provide a little bit more perspective. So, and Tim, totally correct me if I'm wrong, but Holocene is often selected as active because it's post-glacial. So during the last glacial period, you're really changing the landscape. You can have wetter climate, and it's really eroding and modifying fault scarps. So the idea is, if you can see active, the imprint of faulting on a Holocene landscape, on a post-glacial landscape, it must be a pretty active fault. And then the California Division of Dams, I could be wrong with this, but I heard that the 35,000 year is based primarily on radiocarbon dating at the time when they came up with that age date metric. So that's as far back as you could date deposits, in the latest quaternary. So that's kind of why that metric is there.
Thank you. Yeah, and for our class, we don't have any age control, so we're just reading the landscape. So that what Chris said about last glacial maximum, if you look at this curve right here, these curves are marine isotope stages. So that's the kind of ocean water indication of the climate variation, and it's a little bit hard to see, but that peak right there is the LGM at 18,000. So since 18,000 years ago, we've basically warmed, and we're continuing to warm. But prior to that, the last time it was warm was 100,000 years ago. So let's keep going. Let's look at some cool maps. So here's one. Some of these are ones I know, and others are examples. So here's a place. So does anybody want to draw some faults on here for me, or how do you want to tackle this?
Geomorphic features first.
Yeah, so just draw something or comment on it. What do you see? Yeah, fan, old fan. See how it's incised? Others? What else? Oh, okay.
Just mark a scarp.
Yeah, very nice scarp. Elongate scarp. The sun's kind of illuminated from the south. It's a big shadow. So you're looking at a ridge line with the north-facing slope. Next. Yep, some kind of lineament, sort of continuous scarp adjacent to some fan surface. Next. What else? Come on, guys.
Some triangular facets up towards the west side.
Yep, triangular facets. Now remember, we talked sometimes those can be formed by lateral erosion as well as faulting. Somebody mapped a younger fan over there on the right. Come on, what else?
And you can just use your words too. You
Yeah.
don't really have to draw it.
Okay, there's a composite fan. So there's some young and old fans in those brown lines. Where else? What? Just show me some faults, guys. There are some pretty obvious linear breaks. Yep. Where else? Yes, brown, that one on top. There's only 2 people drawing. Come on, pick some more colors. Let's get some more student involvement here. Ah, green. Yes, excellent. Anything else? Come on, you guys can do it. Wake up. Yeah. Yes, dark. I like that big green. Ah, interesting. So what, that last little green on the lower right, do you see a disruption of that fan toe? Purple, I agree with. So yeah, so you guys are seeing it. Go ahead.
I have a quick question. I'm using the big green also with the brown. What is that change?
Good. That I think is basically, that is good question. So see this black zone. Let me get my annotation out. I'll be yellow. So this black or dark gray zone is the active sort of braid plane of the river. So that feature you just highlighted, Jack, is lateral erosion. So it's a scarp derived.
I would say that, and then you see a change in deformation. You know, it almost switches back. Is all I see.
Yeah. Well, those are, this is a key question, is how do we know, are those fault traces or erosional boundaries? Like, how are we going to make that decision? Anyone? Are you students awake? We only have so far 2 students doing anything.
Yep.
So what do you think, Joe?
I've been doing the red line.
Okay, good.
Some of the red lines aren't me. I think that was somebody else working something like up in this area.
So anyway,
Yeah, sorry, I changed my color.
Okay. But how can we make this decision, or what do we think about erosion versus faulting?
I think I would look for things like point breaks, like I marked kind of down here where I thought I saw kind of like a ridge line break right there.
Yep.
And I would look for drainage systems, like how they connect, I would look for like things like wine glass canyons, like how Rich was saying with the triangular facets.
Yep. Yep. So this to me is almost for sure a lateral erosion. That yellow line is not a fault. And probably some of what's on the other side is also lateral erosion. So these environments, any river, but especially this one, which is, you can tell, is kind of a desertic system, they're unstable in their bed. So they just move around. It's like a hose that you turn on that just whips around back and forth. And as it's whipping around back and forth, it's eroding laterally. So you have to watch out for that. And the worst thing is a fault scarp that's a fluvially modified fault scarp, because then you're like, ah, man, it's both. So possibly that's what's going on here on the north side. So let's look. Any comments more?
I'll say that, yeah, these fluvial scarps are really challenging even to experienced geologists, and they can be quite controversial. And back when I was starting in geology, there was this thing called the Beatty Scarp in Nevada that was sort of near, I won't go into the background of why it's important, but there were great debates over the nature of this scarp out in the desert, and they finally had to trench it to really determine what it was, and it turned out to be a fluvial scarp, I think. So.
Yep.
Yeah, and I'd add, it's not always either or. It could be a modified fault scarp, so fluvial and tectonic scarp.
Yeah, and one thing to think of, and I just drew some more yellow lines that are also probably fluvially modified. And what happens, another thing is you can have a fault scarp that's fluvially modified, or imagine you have an uplifting fold or something that's lifting up. So as you're lifting something, you're cutting into the side of it. So you're sort of notching it. And so it's still a result of active deformation. It might not be totally, you know, fault rupture at that location, but it's lifting up. And so actually that's what's happening here. This ridge that has that, like what I'm drawing sort of right now, this ridge that we identified is lifting up. So as it's lifting up and it's in the face of this big fire hose of this river, it's getting notched on its side. So just in the interest of time, I'm going to keep moving and show you guys. So here, this was a project I worked on with UC Davis colleague. This is in there. So here's kind of how we mapped it. And so you guys picked out most of the features. You can see there's some effort to sort of pick out the fans here, these QY, QM, QOs. And then, and so you can see where we didn't map the faults, which is where we decided those were probably lateral, but like up in this area up here where there was some yellow drawn, you know, that is a fluvially modified scarp. But there's a bunch of detailed faulting in here that all those little red lines with dots are on them showing some kind of local normal faulting. So this is part of the Altan-Tog fault in sort of north edge of Tibet, but this was kind of some mapping we did to sort of try to figure out what was going on there. So let's move on. I'm just, you know, please interrupt me, but I wanted to look at a few more maps just to get a flavor of things. So here's one that Rich provided. This is from Jamaica. So this would be derived from aerial photography and LiDAR, Rich?
Yeah, no LiDAR. This is before that, really. There was nothing there. There was air photos, but it's super vegetated as well. So it's field work, walking this trace, and air photo. And
so what you want to see also is notice how he's got his point observations of the tectonic geomorph, notch, shutter ridge, BS. Hopefully no one called BS on your linear breaks and slope, Rich.
Yeah, break and slope.
Yeah, linear drainages, etc. And then you see as we go to kind of, whoops, so then progressive sort of indication of the traces with those linear, those point features tagged. And then here's kind of a little bit more of the, let's say, the quaternary mapping. So everything that's not colored would be like local bedrock. So this is, again, that's kind of trying to isolate the young deposits to assess the degree to which they might be disrupted.
And I'll just add that you know, I mapped the quaternary geology in an effort to find locations to do paleoseismic, more detailed work. There was lots of places where there wasn't a lot of geomorph to map because it was in kind of bedrocky sort of highlands. I'll also point out that there's places where there's no topo because we couldn't find one. So this just gets at sometimes when you're working international, you can't get all this great topographic data. You might not have LiDAR, but you might not even have topo maps. So we had to kind of combine the photos with the topo maps, and the topo maps are of various quality, and it took, you know, several hours in a state geological or in a government office in Jamaica just to get copies of the topos. Like, so it can be challenging, but with all the same techniques, you can generate a map.
Yep. Yeah, so that's cool. And now, of course, you know, this was 2012, so you must have done this 2010 or so, but 2013. So, you know, of course, now we have sort of widespread availability of Google Earth, so we almost always at least have some kind of imagery base, but
right,
may not always be that great. Okay, so let's keep going, guys. I'm just calling out some different examples here. Oh yeah, let's talk about this one. So this is some suggestions that came from Steve Thompson, and it's important for you guys to see a couple points here. So up in the upper right, you can see this final technical report, map of active fault traces, geomorphic features, and quaternary surficial deposits along the central Calaveras Fault, Santa Clara County, California. So you can see where the location is. And then notice this narrative. It's a little bit long-winded here, but geomorphic features are ranked according to a scale of clarity by using the following codes. G1 indicates strongly pronounced features, G2 distinct features, G3 features with weaker expression, and then features of uncertain tectonic origin are queried. The geomorphic codes do not reflect a degree of confidence in the judgment that they're Holocene age. Instead, where evidence for Holocene displacement lays less certain, the map delineates the fault trace as a dotted or queried line. And then the recency or the accuracy relates to clarity of the geomorphic expression, as well as any additional lines of evidence. For example, blah, 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 I'm just moving along. Uncertainty in the location of the fault trace is expressed by varying line types. So it's kind of two ways of grading things. One is the scale of clarity, but the other is the location. So, solid lines indicate well-located traces, less than or equal to 25 meters. Dashed lines indicate traces located to maybe within 50 meters, and dotted lines indicate concealed or inferred traces less than or equal to 75 meters. So you see what I like is there's a qualitative ranking for the geomorphic features, but there's also this quantitative indication from the line work on the confidence in the fault trace location, which is valuable for our work. So let's just look. One interesting thing that came, so this was for the Calaveras, but it follows this Leenkamper 1992 mapping of the Hayward, which is just up to the northwest. And one thing he could do, which was interesting, was look at distance along the fault versus kind of the quality ranking distribution. So you can kind of see where the fault, so this is distance along this axis here from northwest to southeast, the x-axis, and this lower diagram C is what I'm looking at. And so you can see, black, gray, and white are the G1, G2, G3 quality rankings per each 5 kilometers. And so you sort of see he's getting like 20 to 40 features per 5 kilometers, but you can also see sometimes there's a decent number of black ones of G1s, whereas other places like here in this 15 to 20, it's not that great. It's a few, G2s and G3s. And he's also trying to show, okay, maybe that's controlled by the rainfall distribution. So it's a little wetter in the northwest. Does that make a difference? And then also a little bit of the topography, which is probably going to be controlling the rainfall, the orography. So this is another way you can use these quality ratings to sort of look at how the fault is mapped. And I thought that was interesting. Any comments? Okay, so let's look. So just another one, you guys had seen this one. This was from Rich, he showed. So they're mapping in northern San Andreas. So remember this nice coding and the identification of these fault traces in this sort of early LiDAR data that's pretty lumpy because it's a digital terrain model underneath a lot of trees. Let me just look. Oh, somehow I jumped over this one. Here's the Calaveras mapping from a slightly different report, but you can see, again, this final technical report. So this is supported by USGS, National Earthquake Hazard Reduction Program consulting report. And you see the way the lines are defined, sort of well constrained are red, orange are moderately constrained, and blue are poorly constrained. And then the second pass through it is certain, approximate, and concealed. So that's an effort to sort of indicate that certainty. And you can see what I liked in the right here is just the sort of variation, especially this blue here is pretty, poorly constrained, but they thought they saw something coming through there on the air photos probably. And you note here the red is where there's some things crossing. So that's where they were confident enough they might have dug some trenches. So that's nice looking cartography, sort of well documented. Any comments?
Yeah, just one comment. This is Rich. I just wanted to say that I was at WLA when these projects were going on, and several of the examples you have. I just wanted to note that we were working really closely. We had a team of geologists, and we were working really closely with the California Geological Survey, who wanted, to refine the AP zones. And we were also working really closely with the US Geological Survey and colleagues there to just sort of determine where the best sites were for doing paleoseismic work and just to produce better fault maps. So it's really a cool time to be there and really attack all of the main faults in the Bay Area. And I wasn't on this project, but I was on a couple of the other ones. Yeah, there's a lot of good examples from these projects out of that era with really good fault mapping.
Yeah.
This is Chris. I can also add something about this. I believe, I could be wrong, but I think that the area where the fault location is more poorly constrained may coincide with landslides. I think there's a big landslide complex in this area. So, you know, it's an area where the area of faulting was modified by landsliding. It's probably pretty old. And then you have to imprint the faulting on that younger deposit. So it's harder to see the fault in that area.
Yeah, like
if I remember correctly.
This kind of weird topography that I drew in green is suspicious as a kind of a lumpy landslide zone.
Yep.
And yeah, so
it's just the whole golf club there. So is on a big landslide, I think. So anyway,
thing here, yeah.
Yeah. So if you're going along and your fault is pretty clearly expressed, and then suddenly you kind of lose it, there could be reasons for that. Just surface processes that have overprinted the fault, and then the fault has to overprint those.
Yeah, exactly.
Would I, if I can interject, would you gentlemen say probably the most common geomorphic feature that hides faults well would be alluvial fans?
Well, young fans can remove the evidence of a scarp by erosion or bury it. So in some places that is the case, but in others, like in a lot of coastal California, it's the landslides that are the big obscurers. And if you're in high latitudes, it might be kind of glacial related or periglacial related features that are sort of actively covering or removing the evidence of the rupture.
Or lacustrine features in Nevada bury.
Say that slightly louder.
Lacustrine features in Nevada can bury kind of the smaller scarps. And then we were talking about modified fault scarps earlier. So some of the bigger scarps may be preserved, but they may get modified by the high lake shoreline. So looking at the overall geomorphology, you may see younger lacustrine deposits burying smaller scarps, but some of the larger ones may be preserved. And above those larger scarps, you're going to see like the well-dissected alluvial fans that gives you the indication that faulting did occur because you preserved that fan, but then the scarp's been modified. So the lacustrine geology can really complicate and bury things too.
That's a good one. Let's look at, Rich had an example here. I don't know if there's any lakes in here, but here's a couple of examples Rich provided that are, I don't know if there's a lake here, but just this shows using aerial photography in the Quaternary geology and looking at how on the left, the main figure you guys should appreciate shows these, old, middle, and young fans. And what's important is, that where the scarps are disrupting things there, it's solid, but then like across this QFY where probably it's didn't break that fan, that the fan is younger, it's dashed, or maybe it should even be dotted, that would go underneath there. So, and then here's another one from Rich. This is Egan Range. And here would be a place you would be suspicious. I don't know if there is a shoreline here, but you might worry about one given the, valley there and these scarps kind of sitting right on the side of the valley.
Yeah, that's exactly it. The blue is basin fill, and there was a lake in that valley. And the image in the middle, you can see the red line. It's mapped as solid, but I was a young, impressionable geologist at the time. So, but it's the curvature of it is sort of mimicking like how a lake would bend around it, and maintain elevation. So that's probably a shoreline. But then in the photo, you can see numerous different ages of deposits. And the scarp gets bigger as you go to the north, and the deposits go from intermediate age to older age fans, and then even to tertiary pediment where the scarp is even larger.
Yeah. So that's the kind of example of consistency also that sort of goes with the logic of the geology, which is, okay, so based on your read of the the geology we're getting from young to, older fans to this BR would be the tertiary soil bedrock. And indeed, the scarps are getting higher. So that's a pretty good piece of evidence of recurrent active faulting. Something keeps happening.
And then even at the southern end of that trace, it's buried by the young fan.
Yeah, that's right. So it's consistent in both senses. It's not where it's supposed to be, and where what it's offsetting is older, it's taller. So that's one thing that is important for you guys to keep in mind, and I think is a good test of your mapping is that kind of consistency or logical consistency with the geology.
I had a quick question, and it might be better to ask it on the slide previously.
Okay, let me just clear these drawings. Okay, here.
Yes, so we know that there's some type of faulting between the fans because when you start to map the old, immediate, intermediate, and young fans, they have different color or different flow patterns, but you see that they're kind of a break in them, and we did that before with different coloring or whatever we used. But when they're unfaulted, how are the mechanics of these alluvial fans going to look? Because if I didn't really have this kind of knowledge previously and I had to map them, I would just think it's a different colored dirt. So I don't know how they're being offset from their original position to where they are now.
Good question. Well, a couple things. One is learning about sort of desert surface processes, and what we know is that the general assumption, and which seems to be true, is that there's progressive incision. So without even faulting, usually the older surfaces are higher. So like remember from our class when we did the Salt River Terraces, older is higher. So that means if it's higher and older, it's the potential for incision is greater. So these deep channels cutting this old fan makes sense. Whereas there's no significant channels on the young fan except an active channel. The second thing is once you leave that surface out in the desert for tens or hundreds of thousands of years, the surface starts to change. And so we get this varnishing, and then also even this light color could come from the varnish surfaces or the pavements being there, but also eroding into the underlying carbonate-rich soils. And so you almost get these big white ridges. They call ballenas or whales in parts of desert mapping because it looks like a big whale sitting out there, and it's just a bunch of gravel that's cemented by carbonate that was once the soil, and now because of erosion it's sort of been eroded into, but the carbonate's kind of resistant still to erosion, so it sort of holds the ridge up. So I don't know, maybe the others want to add.
Well, just one thing. So the big drainages, so this green unit at the top, the big drainages cut through the entire surface, but these other ones are sort of headwardly eroding into the surface. So it gives you an idea that something had to change along the scarp, either lacustrine erosion or faulting, to cause some elevation change, and then the headward erosion starts through time, and that becomes more developed through time. So in this older green unit, it's pretty well developed.
Yeah, that's right. So on top of just the general incision sequence, the faulting, in this case being normal faultings, drop in the basin down. So that helps drive that increase in, or like the drop in base level.
And
Great
so
question.
if there wasn't any faulting in between these fans, would there not only be no change in elevation, but would there be kind of a less linear line between the fans?
Yeah, I mean, you just over here, you can see basically the transition from the three fans. So, and it's first just kind of elevation based. So Y is low, the QFY, the youngest is lowest, the I intermediate's medium, and the O is highest. And yeah, it's sort of this inset erosion and then some lateral erosion that sort of carves those boundaries. So, we see this in places where there's not faulting. Like if you go back, remember the example from China where we were drawing, that one had same sort of story with this incisional history, right here. So these fans, in the lower right there, are deeply incised. So those are almost, they're higher, but they're also probably the oldest fans. And then this one would be sort of intermediate. And then the youngest one is going out in here, and it's connected to the active channel. So, you know, this would be O, I, and Y for old, intermediate, young.
And there wasn't any faulting in that area, right? So those
That's
are
right. This side is unfaulted.
okay. Gotcha. Thank you.
Yep.
So they can't have sharp contacts between each other, but if you see a sharp contact that's going basically perpendicular or highly oblique to the direction of fan deposition, that could be an indication that something has occurred faulting-wise.
Yeah. So here, like this, these fans up here show some sharp breaks that are sort of perpendicular to the other geomorphic patterns of flow. So those are faulted, but these guys on the lower right probably are not.
Gotcha. Thank you.
Yeah, let's look. Good conversation. We're getting a few people talking here. Let's look at a few more. Let me see. I wanted to show you guys a couple more, and then we'll sort of sum up with some methodology. So here's a cool example. Some of my favorites. I always like to collect these maps. So I went to my office yesterday, so this was kind of a crappy photograph, but this is a strip map of the median tectonic line, active fault system in Shikoku in Japan. And Japan also had a big campaign to produce active fault maps. And so you see this nice strips here. And here you can see there, it's a little bit of geology mapped, but still pretty much only the quaternary geology. So the colors are different, mostly fan type units. They have some landslide mapped, that's on the lower part of this left panel, and then a whole bunch of line work, and then a few point locations you can see in the middle. And then you see this detailed view on the right where we see some of the fault traces, and their youngest fan units, they're not coloring, but they actually are showing the fan shape by that pattern there. And you can see here, you know, that young fan shape is disrupted by the fault, apparently, because it's drawn solidly through it. So I can trust the geologist to tell me that, and that means that's a suspicious, and that's probably why this reference is here, 1970. Somebody must have done a study there. Whereas you can see here, this dashing, or maybe even should be dotted, is implying that there's no disruption of that particular surface. So this is a kind of a pretty example from Japan. I just flipped through. I had a few more from them. Here's another kind of example of how they've drawn it. You know, it's still, this is pretty derived. So it you know, the lines are quite solid, but you still see some support for the line work. Like some of this little symbology here is probably indicating some broken ridge line. And notice also they're mapping some folding. You see this syncline here. So sometimes our geomorphic surfaces aren't just broken, but they can also be deformed or warped. And that can be important. And it certainly is going to be an issue from infrastructure, right? If you warp your pipeline, that's maybe just almost as bad as actually dislocating it. So here's a couple of pictures. This just shows this site here. You can see their mapping of this fault zone. And then I just want to show you what it looks like on the ground or from the air from their pictures. So the main thing is this, look at this little reservoir here. And if you look, here, you can see that same reservoir. So here's the geomorphology. So, you know, like many urbanized places, of course, the road is right on the fault. So that's going to cause some challenges of interpretation, but you see that still they can identify some offset stream channels, as well as there's clearly a kind of a consistently disrupted foot of the mountain here, and some little paleo surfaces. These M's are like little terraces that are sitting up there. So just another example. I wanted to show this one. This came from Chris Madugo. So one point he likes to make is the consistency of features observed along the strike at different scales. And so we want to remember that, you know, any one weird channel doesn't really mean anything, but a group of weird channels probably does mean something. So this is, you know, imagery. There's a nice hillshade, looks like it's a digital terrain model. So the veg is removed. You see a really pretty landslide right in there. Right here is a nice landslide, another landslide in this little trough. And then I can't somehow advance. Okay, so then here is the interpretation. So Chris, do you want to say anything here?
Yeah, so I had a couple points here, just the consistency of geomorphic features. So let's see if I can annotate. So this looks like right lateral offset stream, maybe here a beheaded drainage. And then if you zoom out, you can see larger drainages that have the same type of offset, but bigger. So that's building your case that this is likely a right lateral strike slip fault. The point that I wanted to make here, zooming in here, this was a fault study that was done for us. But, you know, in contrast to what you're doing, where you just are mapping yourself, you're not using previous people's mapping, you just have one line delineating the fault. But what this is showing is all previous studies. So the study that was done for us, the mapping is the green dashes, but the Kelson mapping that was referenced earlier, this is the Calaveras fault, that's this kind of burgundy color here, and then they've got these dashed lines down here. And then there's other mapping in red. And as you can see, they all identify the basic main fault zone, but they all put the main strand in slightly different places. And so this colored area encompasses all the zones into an uncertainty zone. This would be the epistemic uncertainty or the model uncertainty. Different folks put the fault in different places. And you know, there's one right answer. The fault is in one of these locations, but without doing additional work, you can't tell the difference, really. So that's your uncertainty. So I just wanted to highlight, when you're putting your line on the map, you know, there could be some uncertainty to that. And if someone else came and mapped it, they might put the fault location in a slightly different place. And they might also map features. So Kelson mapped these other kind of lower certainty features down here on this slope.
Yeah, that's really great, Chris. And I like that comparison of the mapping, because in a way that's what we're trying to do in our class, is we're going to at least have two sets of lines for each of these sites. And you know, we don't know which is right in a sense, so, or you guys don't. And so it's really important to have that open mind, see what you see, what are the features that support your line work. So
right, and a lot of times, like if we look to the left of the mapped imagery, you know, you could have a trough along the fault, and you don't know which side of the trough to put the fault on. Here it could be the bottom or the top, or it could be both. Some folks will choose both. So the green lines choose both, the red line just chooses the top, the burgundy may choose both. So don't stress if you know, you have a linear feature and you're trying to decide which side to put the fault on. It may be both, and maybe one side or the other.
Now, can this, I'm sorry for interrupting, but could this also kind of go back to that the one talk that we had about mapping faults as zones? You know, like as instead of like lines, like mapping them as more like wide areas.
mm-hmm.
Right, and then there can be a zone of deformation as well. Yeah.
So let's just, I'm sensitive about the time. I wanted to, I have some more cool stuff, but let's just kind of summarize a little bit. So one thing is this information from Tim, and just reminding you guys about the line, the sort of conventions of line location and scientific confidence. And so that's something we're going to provide to you. Chelsea's been working on sort of a little bit more guidance on exactly how the lines should look, because even though it's what you've done is fine, I think even if we have a little bit more coherent cartography, it'll just help us all feel like we're mapping the same things. The other thing is just a reminder from McAlpin, his flow chart on, you know, the sort of how to do this, you know, regional or local photogeologic, but you guys are also doing mapping on high resolution topography with emphasis on quaternary deposits, map features that cut deposits or landforms, and then try to figure out what it comes from. And, you know, is it cultural? Is it non-tectonic? Is it tectonic? And then then the rest of this flowchart is then what to do, how to make an excavation, more site-specific study. But, you know, that's sort of trying to characterize what we're doing. So let's look maybe one more. Well, let's see. Here's one from, this is a project from Baja California. This is in southern tip of Baja. So you can see this mapping is including the quaternary surfaces as well as the traces and how they're sort of discontinuous. The white line is showing the fault trace, and where we, you know, thought maybe they became inactive along some of their extensions, but notice it's pretty discontinuous on the left side. So that's that. Another example maybe interesting is this one here, which is something one of my students worked on, which is in these urban environments is kind of a funny outcome of a lot of this delineation, which is that it actually produces places where it's a nice place to have a park. So suddenly your mapped fault zone becomes an amenity. So it's actually opposite of what you think is going to happen, because you think, oh, who would want to live next to a fault? Well, it turns out in a lot of places in California, everybody wants to live next to the fault because it's actually open space. So that was kind of an unexpected outcome of sustained fault zone mapping and zonation. So we're right at 10:15. I have a couple more examples to discuss or present, but maybe I can put this one on. This is from Spain. This is kind of a complex, sort of an ugly fault zone, but you see an attempt is made there based on, this is a digital terrain model from their LiDAR, sort of mapping these quaternary surfaces and this kind of ensemble of features or indicators indicating three main zones along this Alhama de Murcia fault. So any comments or questions to sort of bring it to a close?
Very informative presentation. Thank you.
Well, thanks. Yeah, it's, you know, I felt like it's sort of like we're coaching, right? So we got to look at some film. So we're looking at some film here and seeing how it's done, and want you guys to just think about that yourselves, you know, just to help move towards that sort of professional standard like we.
So so moving forward, I definitely I did not use the USGS standard mapping symbols. I found a PDF that has all of them, and I was wanting to see if I could send it to you to see if like this is kind of where you're getting it.
Yeah, I think there, you know, the USGS, like as Tim shows in this one thing here, the solar et al., like this is a whole industry of cartography, like how to show every possible thing, the solar et al. USGS OFR. But so I wouldn't say we don't need to overcomplicate it, but at a minimum, we want to probably use solid and dashing with queries, maybe a little bit of change in weight.
I'll compile a list so that, or like pretty clear set of short guidelines so that you can use, and I'll try to get this to you hopefully tomorrow, if not definitely on Monday, so that you can start incorporating it quickly, and then we'll spend a few minutes on Tuesday discussing it.
Yeah, and this is Chris. I think, you know, for mapping standards, for just the geomorphic mapping, that's less important. We saw so many different examples of how people identified geomorphic features that they thought were related to tectonics. But then as you move to that final fault map, if we can get a more standardized way to show the quote unquote faults, you know, that would be really helpful.
All right, great.
Yeah, so don't wait for this description before you start your geomorphic mapping, because there's a lot you can learn about the landscape using relevant symbology, as Chris was saying.
Yeah, that's cartography, which is different than the information. It's just how it's represented. But we do think that as you work and you start to define how it's presented, we'll want to be a little more consistent. So anyway, I'll share this with you guys. I had a few other examples. This one was something I did with a couple of my students, which was just comparing different sort of field versus USGS versus completely remote mapping. And this just is one example where it's the same piece of ground, but the top was mapped by USGS. So you see this kind of discontinuous features with the point-based tagging. The middle is field mapping, so we walked it. So we had things being a little bit more continuous.
Are you sharing your
We
screen now?
can't see you, Ramon, or we can see you, but not the screen.
Sorry, I was so excited to talk. I'll just show this, but sorry. So maybe you can see it now. So this was the different kinds, different sources, and then here was the comparison of the mapping. So same place mapped 3 different ways. Top is USGS, mostly air photo based. Middle is field based. Bottom is office based. And the bottom had access to these LiDAR data, but the upper 2 didn't. And so you can see what's consistent, and that's a test for our certainty is do different mappers get the same features, and then others are, you know, you see these blue lines in the bottom are a little, you know, maybe how well are they supported, we don't know, but at least we know they're not as confident because they're indicated as such. So anyway, I could talk probably all day on this, so I'll stop, but thanks for the chance to share, and hopefully that's useful.
Thank you, Ramon. Yeah, if you send your slides, I'll get them on the website quickly so students can look, and then I'll later today, I'll post the lecture today on YouTube and link it to the course website.
Yeah, and I'm just looking at the file that Joe sent. This is the right sort of thing to be looking at, but as I said, we don't want to overcomplicate. This isn't a class about cartography, you know. So we don't
I was just looking at like the faults section. I think that's it was kind of close to what you put up on one of your slides.
Yeah, so this is cool, but this is like a whole book, right? So this is how the whole USGS is supposed to map, but it's all there, so I don't disagree with it. And it shows kind of the standard mapping cartography standards, so it's good, but we're not quite at the point of needing to go this crazy.
Yeah, I think that was a pretty big barrier for me, was trying to figure out, you know, how exactly to represent what I was seeing.
Right. Here you can see, you know, some very nice looking, you know, scarp on low angle fault, blah, blah, blah. So there's a lot of maybe inspiration here, but I think we don't need to go quite so detailed unless you're ready to do it.
Oh no, I think I'll stick with the slides. All right. Well, thank you guys. Thank you for your time.
No problem. Yeah, I have to excuse myself. Also, I have to go to a class meeting, but yeah, so just like I said, sort of aficionados of mapping is something we all want to become, and find out ways to judge quality. So I'm going to take off, but I'll get this to you right away, Chelsea.
Okay, I'll say if people have any questions.
Thanks.